Hey guys, so I know a couple of you guys have been worried about not getting enough practice. I know that there's that one problem that some TAs gave out and others didn't. That problem's pretty good. It's okay. I won't say pretty good. It's okay to kind of get the ball rolling, but I think you guys could use some more. And I know you guys feel like that too. So here's some problems that I made over the summer for 118B. Funny story, actually, I don't think I ever actually sent these out because I didn't know how to export I did not know how to export PDF to, or sorry, ChemDraw to PDF is what I meant. I didn't know how to do that because I make these on ChemDraw. And I don't know how to do that export, but I actually recently, well, actually today, I found out how to do it. I asked a friend, they told me. So I'll go ahead and send this out. Before I used to just like make things into JPEGs and then compress them into PDFs and it would make everything look really ugly, but this looks nicer. So yeah, in this document, you'll find 6 problems, hopefully in increasing difficulty, although all of them have their own sort of things. At the bottom here, I have sort of a chart to kind of help remind you guys of what to think about, what to look out for. You know, what do some regions mean? And I imagine hopefully this part here is a little familiar, like this corner here. This stuff down here and this stuff here must be new. So I imagine the first part of this video, we will go over this, very quickly, maybe 30 minutes tops, just go over everything again, remind you guys of what those things mean. And then afterwards, we'll go through all the problems. I'll let you guys know now, I'm not very keen on making answer keys. I don't think answer keys are very useful. I think it's better for you guys to solve problems and ask each other and, confidently come to the answer yourself that you're right. But I know that, that's a hard thing to do, especially as a introductory student into organic chemistry. So this video, I guess, serves as the answer key for this. So if you want, you can try this on your own and then click through the video to find where the answers are. I highly recommend, though, that you guys watch it through to the end. You never know, you might learn something new. Cool. All right, so let's just go into the review part. So again, you guys hopefully remember much of this stuff back from 118A. If not, it's okay, because the point of this is to remind you guys of what this stuff is. Okay, so HNMR, what does it do? What does it tell us? HNMR basically shoots magnetic waves at protons, or at structures, and protons absorb them, and we see where those protons show up, right? In general, protons that have a lot of electrons around them, or shielded protons, are on the right here at near zero. Very deshielded protons are, literal protons, like hydrogens that have proton character, more deshielded show up on the left side, where we tend to see that. You can see that's like kind of a range, going from more shielded to more deshielded. The general idea is over on the right here, we have very broad information as to what can be the functional group. As you can see, like there's a lot of stuff littered around here, but as we go more into the left, it becomes very, very specific. And you know exactly what you're dealing with when you're at this side. So let's just start with this. So 0 to 1.5, we have normal alkyl bonds. So this is, I call like the aliphatic region, or the bland region, or the boring region, because all this really tells you is that there's a carbon bound to a carbon, which, surprise, it's organic chemistry. That shouldn't surprise anyone. That's the whole point of organic chemistry, is to have carbon bound to carbon. So normal sp3 carbons bound to each other, which have no dipole, no nothing, are just going to show up in this region. Truly, the only like defueling interaction in this area is protons deshielding other protons. So like a CH3 deshielding a CH2. That's about it. This is what I also think of as like the glue area. Like if you're ever missing a piece to glue parts, like let's say you have like an alkene and you're trying to glue it to something else, it's typically glued onto something else with like another carb, like an alkene carbon or something. So normal alkane chain, alkyl skeleton. This is from 0 to 1.5. Very, very boring. I tend to never start here because it doesn't really tell me much. But once you leave 1.5, you get a lot of information. One of those first pieces of information being 1.5 to 3, which is the alpha hydrogen region. So what is the alpha hydrogen? Alpha hydrogen is a hydrogen that is located next to some kind of pi bond. So the carbonyl pi bond next door, there's a hydrogen. Alkene pi bond next door, there's a hydrogen. And then alkyne pi bond, hydrogen next door, that's the one we're looking at. Okay. Another way to think about it is that if we took, sp3, if we took one of those sp3 carbons and turned it to an sp2 carbon, that slight change in electronegativity causes a slight dipole, and that's that dipole that we're measuring in the deshieldedness of these alpha hydrogens. Okay, so going from sp3 to sp2 sp3, right? That's what's causing these protons to show more deshielded. Actually, in this case, right, sp3, most deshielded carbon or most electronegative carbon possible still shows up about 2 to 3. The alkyne proton also shows up here, which is a little bit interesting, but I don't think it's a hard one to remember. You just kind of remember, next to a pi bond, and then for the alkyne actually on the pi bond, the hydrogen shows up there as well. Okay, so that's this region here. The only way to get a carbon or a proton more deshielded is you got to make that atom bound to carbon something not carbon, because even the most electronegative carbon cannot escape 3. So what do? We take that carbon, sp, sp2, or sp3, and we change it into a heteroatom, nitrogen, oxygen, or some halide. So when we have a CX bond, CO bond, CN bond, those hydrogens on those carbons are incredibly deshielded from 3 to 4. Everyone's favorite region, right? Like you see 3 to 4, you know exactly what's going on. There's no no confusion, right? We don't have to worry about what pi bond it is. We just look in the formula. Is there an N? Is there an O? Is there an X? Pretty much can figure out what to do from there. After this region is kind of counterintuitive, because you see a pi bond, you think, wait, weren't pi bonds 2 to 3? Well, protons that are actually on the pi bond, so these were alpha to the pi bond, protons that are actually on the pi bond are vinyl protons. These guys are affected by something known as the anisotropic effect, which is where the electronegative field, the magnetic field causes another magnetic field because of the pi bond. Don't worry about this too much. It's for NMR PhD students should understand it. You guys are Orgo 1 students, so not a big deal. But basically, when you put a magnetic field on a pi bond, it creates its own magnetic field which doubly deshields these protons, which is why these protons show up higher than you would expect them. It's just extra the case for the aromatics. The aromatics have like a stronger magnetic field. If you're in physics 7C or 9C or whatever you take, you can think of the electrons as a current. And so when the magnetic field is sort of exerted on the current here, there's like another magnetic field that shows up. It's just, cool physics stuff. So these protons end up being just more deshielded. Trust me, there are patterns for these, so you don't have to remember like what kind of alkene shows up and what way. As long as you understand the patterns, you'll know what to do. Actually, for the benzene one, we actually have the patterns down here. Whether you have a monosub, disub, or trisub, there are certain things you can look for. Monosub is very simple. 5 hydrogens can only be arranged one way. Looks like a mess. That's not at all difficult, in my opinion, to figure out. So as long as you know that, you'll be fine. Disub, though, there's 3 varieties: para, meta, ortho. And there's certain things we look for to know which one it is. The easiest of the 3 being para. Para has a symmetry line about it. And so because of that, these protons here tend to be the same. I know I put X and X here. It should be X and Y. So think about this as X and Y. I think when I made this, this document I made while tutoring someone, and I changed it to X to exemplify something, but I never changed it back to Y. So think X, Y here to understand how we get the 2H2H, because if it's XX, then all these protons are the same proton, but that's not the case, right? We want to know differences. So X and Y, right? We have this nice 2H2H split because of symmetry. Now, if I take that one of the like X groups and I move it to the right here, so I get this kind of splitting, we get meta. And so meta is like the beginning of mess. You can see ortho is actually a literal mess here. I guess actually we can start with ortho. If you have 2 protons two X groups next to each other to get this ortho splitting, you really cannot really read this region. It's like totally a mess. All the protons tend to actually clump together to make a 4H kind of mess. If you see a mess, you know that it's got to be some kind of ortho thing. Meta is also a mess, but the one thing that makes it better is that this one proton here that's flanked by the 2X and the 2X groups here tends to show up as a singlet. So my sort of advice for people when they do disub splitting is just look for either the 2 towers, the 2H towers, look for the 1H meta peak. And if you don't see either of these 2, then it's ortho. As simple as that. The last one that I kind of care about is the trisub arrangement. This trisub arrangement in particular, again, think X, Y, Z here, not XXX. But if it's X, Y, and Z, you get 3 nice singlets. Very, very simple. The only other trisub is if you move one of like this X group over here, so that 2 of these guys are next to each other and one of them is away. That one is it's very similar to it's really similar to ortho, where you just have 3 hydrogens that are kind of just clumped together in a mess. Cool. Don't worry about this too much. I went through it fast because we won't care about it until midterm 2 anyways. So you get a reminder of all this if you just, continue working through the class. It's just in case you do practice problems, you see it, you know what to do. Cool. The last region is about 8 to 11, which is just going to be the not tyrosine, sorry, phenol, aldehyde, this purple proton, not the green one, this purple one. So phenol proton, aldehyde proton, and carboxylic acid proton. Two of these protons are actually very interesting, the carboxylic acid and the phenol, because they're actually OH protons, like this OH and this NH. These guys here, because of hydrogen bonding, get really weird peaks, and they can show up about 0 to like 9. Which kind of scares people because they're like, wait a minute, 0 to 9, so it can show up anywhere. Yeah, it can, but hydrogen bonding also helps us out because it broadens the peak out a lot. So whether it's an OH, an NH, or one of these guys here, you get really broad peaks. So as long as you can identify a broad peak from a not broad peak, you will know that these structures are viable and at play. Cool. So that's HNMR, and hopefully, again, that was like a review. If not, don't worry, we'll reapply all this back when we do the 6 problems. What's new to everyone probably is going to be the CNMR region or the CNMR material. Here's what I'll tell you. If you treat the CNMR like it is a advanced IR, you will do well in this class on the NMR portion. Do not try to couple, like recoupling or anything, or try to solve structure from CNMR. I think of CNMR solely as like, can this functional group exist? And the answer is pretty much always yes or no, like immediately. So let's just get right into it. CNMR, right, 0 to 60. This is truly a useless area, in my opinion. You could probably even go 0 to 80, honestly. Really, or no, yeah, 0 to 60 is good enough. 0 to 60 is truly useless. It doesn't really tell you much. The reason why is because we get CC, CO, CO, CX, which that's not really helpful to us because we can already tell that from the HNMR anyways, right? This is stuff we already get from the HNMR anyway, so this kind of bond isn't really helpful for us. What's helpful in the CNMR is stuff that we cannot immediately elucidate from the IR or from the HNMR, and we immediately see it from about 70 to 100 or 80 to 100, whatever we want to use here, right? With the alkyne, because in the HNMR, it's ambiguous whether we have an alkyne, alkene, or carbonyl, but in the CNMR, we tell immediately. IR can also tell you, right, if there's a triple bond, but the thing about the IR is that IR can only tell you if it's C triple bond C or true super bond or C triple bond N. So both of these are sort of in contention. The CNMR tells you immediately. If it's 70 to 100, it is the alkyne. If it's 100 to 140, really for the nitrile, it's about 120 is where the nitrile shows up. That is going to be a nitrile. So again, another advantage to using the CNMR. The other thing you might see, as I said, look for line pairs. So not lone pairs, line pairs. What I mean by line pairs is that keep in mind that the CNMR is studying individual carbons and not individual functional groups. So that means that if I want an alkyne, I need 2 lines because 2 carbons in an alkyne. Same thing with an alkene, 2 carbons in an alkene. For the nitrile, the one exception around 120, you get 1 line because there's only 1 carbon in there. So number of lines is number of carbons. And so if we have, double bonds or triple bonds, we need pairs, right? That's just going to be the case. So 100 to 140, double bonds. Benzene also shows up here. Benzene is great because benzene has 6 carbons that are double bonded. So you see what I like to call this like a band. You see like a band of carbons from 100 to 140. That's almost always indicative of a benzene. So you can use this on top of looking at the HNMR, right? Over here in this region to make sure that it is actually aromatically active. That's always great. After that region, 160 to 180 is what I call the acyl derivative region, which is basically all these structures here: acyl halide, ester, acid, amide, and then hydride. Really, the cool thing about this part is if you compare it to 200, which is just ketone and aldehyde. Remember, back in 118A, we couldn't tell the difference between ketones and esters. Remember, IR and NMR failed. So IR and HNMR failed at telling us the difference between a ketone and an ester. And now we see it exactly clear. If we have a peak at 160, we know it's an ester. Having a peak at 200 is going to be a ketone. Always look out for that. I remember people that I tutored last quarter, or just people that I tutored in 118 in general, they ask if CO2 in the formula is good enough to tell you that there is an ester. The answer is sometimes it is, right? But now that you know CNMR, you don't have to ask this question anymore, because if you see CO2, just look in there, right? If there's something here, it's probably an ester, right? If you see CO2, but you only see a 200 line, you know the professor's trying to pull a fast one over you, and it's like a ketone with like an oxygen somewhere down the line, like a ketone ester kind of idea. Oh, I should have made one of the problems. Sorry, I should have made one of the problems that up there look like that. I think at the end of the video, I'll do a quick little gallery on ChemDraw. I'll draw up a bunch of stuff that you guys can look at. But yeah, cool. So that is the idea behind the NMRs. And I know I went through this very quickly. It's again, If I spend an hour explaining all this, right, then and I do the problems, this video can easily get into 3 hour range. I want this video to be relatively, medium in length. So, went through quickly with this, but don't worry, we're going to apply all of this right now on the problems. So let's go ahead and do the problems. I highly recommend, so I'll make this document available, of course, with the video. Highly recommend you guys try a stab at these first, using this page here to help you out most of the way. But I imagine, again, it's been a long time since a lot of you guys have taken 118 A, and especially, just NMR in general. It's a hard thing to remember. So my personal opinion is you guys maybe do the first one with me, and then do the rest. But by all means, do whatever you want to. If you want to try all of them and then consult with the video, that's also great too. And then for those of you that haven't done NMR a long time, let's use the first one as sort of a model of how to do the rest of them. Only thing I'll advise the people that want to try on their own is remember to do DOU. And if it's applicable, right, look in the CNMR for functional groups afterwards. Okay, so if it's applicable. So actually, let me explain what I mean by applicable. One thing that you'll notice here, actually, let's do DOU first. So go ahead if you want to, go ahead and pause and try this on your own. But for those of you that want to work on this with me, let's go ahead and do this. So the first thing I mentioned was do a DOU, which is 2c plus 2 plus n minus x minus h all over 2. So we plug things in, right? Carbon times 2, that is going to be 8 times 2, 16. Plus 2 is 18. Plus 0 minus 1 for the bromide. So 18 minus 17 is 1. No, sorry. 18 minus 1 is 17. Sorry, let's do that over again. Sorry, I'm really bad at math. 2 times 8 is 16. Plus 2 is 18. 18 plus 0, 18. And then 18 minus 1 for bromide. So that's 17. And then 17 minus 17 hydrogens, that's going to be 0. I apologize. I'm really bad at math. I hope I didn't confuse anyone with that. But the answer here should be 0 degrees. So there's no unsaturation whatsoever in this molecule. But let's understand what a degree means in the first place so we know what we missed out on. Okay. 1 degree means some kind of double bond, whether it's a carbonyl or an alkene, right? Or it means some kind of ring. So 5-membered, 6-membered, 7-membered, doesn't matter. Any ring size will work here. 2 is any combination. So double bond, ring, or ring, answer your phone, right? It can also just be a triple bond of some kind, whether it's internal or terminal. Okay, so one of these two. 3 is any combination of these guys of 2 degrees and 1 degree. It can be 3 triple bonds, right? Or it can be, a triple bond and a single bond, or sorry, a triple bond and a double bond. Anything, any possibility is possible there. I only tell people to remember 4 degrees because 4 degrees can be a ring with 3 pi bonds. That's a benzene. So 4 degrees is another way to, of assessing, is there a benzene ring possible? So why is it important that we do DOU and then look into CNMR? Because if we look at the functional groups in general that are elucidated by CNMR, notice something. After we leave 60, we have triple bond, double bond, and double bond, which is, pretty much if you have a DOU, CNMR will tell you what that DOU is, pretty much, right? So any degree of unsaturation that's, part of a functional group, CNMR will tell you immediately. But if there's no degree of unsaturation, CNMR is useless, right? Because again, CNMR, the only useful part of CNMR is the unsaturated part of the CNMR. So other than that, I'm not really going to care, right? This problem with 0 degrees, I'm going to go ahead and ignore it. So if you want to write this down, or, write this part down, or, I'll put here any combo of 1 and 2. I'll go ahead and save this screen if anyone needs it, but write that down if you have to. Cool. So there is 0 degrees, a completely saturated molecule, no funny business going on. So now that we know that means CNMR is kind of useless to us. Now all we can do is really just focus on the HNMR. So I wanted this first problem to mainly be HNMR because I just wanted you guys to, for those of you that are working ahead, I wanted you to just like have something from 118A, right, to remind you guys of. And so this is a great starter molecule. What I would do then, if there's literally no degrees of saturation and there's no functional group we can find in the CNMR, I would just look at the things in the formula, right? The fact that there is a bromide and oxygen, that's the fun part, right? There's carbons, sure, but bromide and oxygen are the fun parts of this molecule, because at least for the bromide, there's only one way bromide can show up. It shows up as a CBr. And for oxygen, there's two ways it can show up. It can show up as an ether or it shows up as an alcohol. So of these two, we can actually immediately figure out which one's likely, right? Remember what I said about alcohols for the HNMR, right? What do alcohols look like? Alcohols in the HNMR, broad peak. So no broad peak, I don't see anything broad. There is no alcohol, this has to be an ether. So even without the CNMR, I mean, this is why like that 0 to 60 region is kind of useless for us in the CNMR, because we could have just figured this out just by looking at the formula and just thinking intuitively, right? So that's why it's not very useful to us in this case. But, you know, even with that, right, we can still make this a problem work. So in the HNMR, right, we have a CBr and a COC. So we have an ether, right? Where do CBRs and CO bonds tend to show up? So look back at the chart if you have to. CO bonds and CBr bonds, relatively deshielded, relatively electronegativity bonds, or negative bonds, those guys are going to show up 3 to 4. And look at that. Nicely, we have 3 peaks in that region, which associate with the 3 carbons that are bound to these heteroatoms. So already off to a great start, right? We can already tell that, you know, everything is lining up just as we thought. Now, the one part that might be hard is that we have 3 peaks, but we don't know necessarily which carbon, which hydrogens associate which of these carbons, right? Like, how do you know for certain that this quartet carbon, right, or this quartet hydrogen is on carbon 2 or carbon 3 or carbon 1? I think actually with a little bit of intuition, you guys can probably make a guess. I think at the very least, you guys can make a guess as to which one is C1. So try to use some intuition, think no more than 5 seconds, right? Which carbon do we think is likely, which peak do we think is likely to associate with carbon 1 of these 3 peaks? Which one is the most likely to associate? So again, just like we did earlier, where we said 3 to 4 is deshielded, and we have an oxygen and a bromine, which are deshielding, you know, units. That's why we know to look 3 to 4. Let's also think, right? Carbon and bromine, that is a polarized bond, but it's not necessarily as polarized as carbon oxygen. Carbon oxygen is way more electronegativity, or it's way more electronegative than bromine, right? It's way more electronegative than bromine. So I think that oxygen has the capability of deshielding more than bromine does. What that also then means then is that you see these 2 protons here and this guy here. These guys are really high up and this guy is really low. So my guess then is that of these 3, which one is likely to be C1? I think the 1H triplet is likely to be C1, because again, deshielded proton, right, must be next to a very electronegative unit. And relatively speaking, that is less deshielded. It must be next to the less deshielded component. Okay, so C1Br, right, is likely to be this 1H triplet, which means that these guys here are likely to be on our oxygen. Cool. So that's, you know, you don't need to know too much crazy theory to solve this, but we can make pretty good guesses as to what goes where. Okay, cool. So I can already start to think of 2 sort of pieces here. One piece is going to be this 2H quartet over here next to oxygen, with also this 1H pentet. I use these squiggly lines here for something that I like to call uncertainty, right? Uncertainty, because I'm uncertain as to what's there. But I know for a fact that this is a CH2 and this is a CH, right? I also know that there is like a CH going on over here with a bromide, right? And there is a green proton here. And again, I'm uncertain as to what's there. Cool. So we've gotten quite a bit, you know, of information. We've got 2 pieces right now, a lot of uncertainty, but some of this uncertainty we can break down. For example, if I look at this 2H quartet, right, of the 3 peaks, right, this 2H quartet is a little bit interesting because that means it has 3 neighbors, right? But one side of that 2H is blocked off, right? So one side of this 2H is an oxygen. So what does that mean about this side? Right? If it's a 2H quartet and one side of this 2H has no hydrogens, what does that mean is true with the other side? The other side must have all those hydrogens then, right? That makes sense. Sorry, my throat's a little dry. That makes sense to us, right? If there's only one space for those 3 hydrogens to go, they've got to go on the end there. And one carbon can totally accommodate for those 3 hydrogens. So when we look at this is a CH3, a terminal end of a molecule. I look here, I have a 3H doublet and a 3H triplet. Which one of these peaks most likely corresponds with this guy here? Well, if this 3H has two neighbors, right, that must mean that it is a triplet. And so this 3H triplet here is likely to be the guy next to the 2H quartet. Now this over here, this is actually a very common thing over here. 2H quartet and 3H triplet is almost always going to be an ethyl. So ethyl is very well characterized as this. And specifically in ethyl, where on the other side of the ethyl, there is no protons, right? Because it's a 2H quartet. So it can only have those three guys as a neighbor. Now, sometimes you can have more people. So let's say that, it's actually this here, a propyl piece. Propyl piece is identified as a 2H multiplet of some kind, or 2H pentet, right? But you get the idea. If you see a 3H triplet, okay, a 3H triplet, this is really all you need to really notice. 3H triplet must mean a CH3 next to a CH2, and then the CH2 can have anything next to it, right? We don't know. But for sure, a 3H triplet must be next to a CH2. So first little trick there, right? Actually, you could have noticed that at first, the 3H triplet, and I made that, distinction just off of that. Cool. So one side of our molecule has been figured out. Now we have two other sides that we need to figure out, okay? And that's this, that is going to be the 1H pentet. Now, the 1H pentet is a little interesting because the pentet can be resolved in two different ways. So I'll draw it generically over here, but the pentet can be resolved in two different ways. One way it can be resolved is CH2CH2. Okay, because again, there's a CH2 and a CH2. 4 protons. The other way is if there is a CH3 and a CH. So I'll draw the two models again. Again, pentet means we have 4 neighbors, 2 ways to resolve this. In most cases, you can't really tell sometimes. You have to just kind of guess. But actually, in this case, we know immediately which one it is. We know exactly which system this is. So which one's it going to be? Again, don't think about this for more than a couple seconds, up to 30 seconds, right? Just look at the H&MR. Which one is it going to be? So the reason why I say don't think about this for more than a couple seconds is because if it's going to be this system here, CH2CH2 or CH3CH, then that means that these hydrogens have to exist in the system, right? Another way of saying this is that CH2CH2, there's got to be 2 CH2s in the system that'll accommodate for that. But when I look in the system, or if I look in the NMR, look at that. I only have 1 2H, and I've already used it. I had 1 2H and I used it. Immediately, it's already gone. So in order to have this other CH2CH2 system, there must have been 2 more CH2s. But those CH2s don't even exist. So in this case, this system is impossible. It's got to be the CH-CH3 system. Okay, so I know now for a fact that there's got to be a CH3 and a CH over here. So hopefully the logic follows there, how I'm getting to that point. Okay, so there's got to be this kind of thing going on here, which is great because now we have another terminal end. And if we think about CH3, right, if we think about CH3 on this, there is only one other CH3 in this molecule. Oh, what? Sorry. Oh, sorry. Give me 1 second. Sorry about that. Had to talk to someone real quick. Where was I again? Oh, right. Okay. So just to quickly recap. So I'm going to go back more than I need to probably to recap this. So I think at this point we were talking about, yeah. So on the left side, right, this brown proton here, burgundy proton, right? It's got to be CH2, or it's got to be CH3, CH, right? It's got to be one of those two systems. And just looking at the NMR, right, there is not enough CH2s to accommodate for the system here. So it can't be this guy here. It has to be CH, CH3. So hopefully that follows through. The other thing that's nice about this is that of the CH3, there's only one left. There's only one CH3 left. So that's great because now we know for a fact this guy here has got to be this guy here. No hesitation. So that's great. We know for a fact that this CH3 is this one here. Now the harder one of the two, obviously the CH, well, I guess it has to be, it's kind of obvious that it's a harder one because this one was so easy, right? This CH3, there's only one left, right? So we knew which CH3 had to go here. The harder thing to do is to say who this 1H is in particular, because we don't have only one 1H in the system. We actually have 2. We have the 1H triplet and we have the 1H multiplet. So this is where things get a little bit tricky because we don't know which one of the two it is, but we can figure this out. Okay, we can figure this out. Okay, one way to do this is to think, okay, if I put the green 1H over here, right? Actually, let's do this a different way. So this 1H triplet, we know associates with the bromine. Okay, and the bromine still has like 2 areas of uncertainty that we still have to figure out. So it's still got a little bit of work that needs to be done there. Okay, the other 1H proton though is a 1H multiplet. So what color can I give this? Look at this orange. And this 1H multiplet actually is a very interesting 1H multiplet because there is another peak on this NMR that actually helps us solve this, what this 1H contributes as a structure. So think about what's the only other peak that's unresolved and how does that one peak, resolve itself with the 1H multiplet? The only other peak is a 6H doublet. And hopefully, if not, I'm teaching you now, whenever you see a 1H multiplet and a 6H doublet, this is known as a coincidence peak. And so why do we call it a coincidence peak? Or why do I call it a coincidence peak? Because whenever you see these 2 peaks coinciding on the same NMR, it is 99% of the time an isopropyl piece. So there's a couple of these guys, coincidence peaks, the other one being the 3H triplet and some 2H multiplet of some kind, right? That's the ethyl coincidence peak. This one is very, very strict though. 1H multiplet, 6H doublet, you pretty much know it's always going to be an isopropyl. Now I always get a question of like, is it possible sometimes for it to be not that? Like, is it possible for the 1H multiplet, 6H doublet to not be that? And the answer is yeah. But that's the structure that you can probably think of for it is non-intuitive. It requires a lot of carbons and hydrogens, and it doesn't really make sense that someone would bother you with that. A good professor is going to make you guys rely on, structures that are generalizable and that ones that you recognize from practice. Only a really bad professor would ask you something harder than that. Cool. Anyways, so isopropyl is what we can figure out from these 2 pieces here. So this just becomes a sort of like, what's a building game? This just becomes like a Lego, like which Legos would make sense. So what do I mean by that? So now we just have to figure out, is it going to be the orange H there? Or is it the green H? So what I would do is let's say I've already drawn the orange one, I would draw on the orange one. Okay. Now that orange peak works, right? The 1H multiplet next to these guys here and next approach on there. This could work, but there is a problem with this. You guys see what the problem is? There's actually a pretty big problem. So even though this piece fits and it feels great and it feels nice, this peak, this structure fails to integrate the bromide. So even though we really want to include, right, this 1H there because it feels great, right? Very quickly, this structure cannot fit because, it does fit, but it doesn't make sense because how do we include the bromine piece now? There is no uncertainty left on the rest of our molecule. This is a complete molecule. So you've managed to complete the molecule, but you've left out a piece of the molecule. This is one of the ways that you can prove to yourself something doesn't work is when you're at this kind of crossroads where you have to figure out which 1H is it or which 2H is it or which 3H is it. You just throw it in and you see if it works. Sometimes you just got to Hail Mary it. And in this case, I Hail Married it, but I Hail Married it in the wrong direction. It didn't work. But that's okay because this is information too. It tells us that for certain, it can't be that the 1H is there. That's good. That's good to know. That must mean then if it can't be the orange 1H, it's got to be the green 1H. It has to be the green 1H. Okay. So it's got to be that the green 1H is here. And so if the green 1H is here, that must mean I drew it in, but that must mean that the bromine is here. And so now we've gotten one side of uncertainty figured out, right? And so what's left is this piece here and the isopropyl piece, right? So this is all we got left now. What do we got to do? All we do is connect our last 2 pieces, which is the isopropyl and the bromide. Cool. So this example, I imagine it could have been difficult because of that 1H point, right? It's not very, immediately obvious which one to do, but that's the point of NMR, right? When people actually do NMR, we're just like building things, like we're just making guesses, right? We're taking leaps of faith to make sure that we're right. And again, sometimes the leap of faith won't work, but that's information that tells you if it doesn't work, don't do it. Try the other one. In this case, noting that this would complete a molecule without incorporating this 1H helps you figure out immediately what to do and finish this off. So this structure, although it is like a 118A level of NMR, this structure is a 118B structure, actually. So this bromide halo ether, we call it, this halo ether, you can make with 118B chemistry. So that's why I decided to include it, because it's a valid structure. Most structures that you will get in this class are going to be structures related to material you're working on. So you can always take guesses. So imagine you see a bromo and oxygen again, try the halo ether arrangement to see if that works. Okay. And so halo ether means specifically when they're next to each other. So vicinal halo ether is really what I should be saying. Cool. So first problem down, hopefully that wasn't too bad. And you guys had a good time with that, and it makes sense. So with that sort of structuring, right, I think you guys can definitely try the rest of these on your own now. But again, if you want to do a couple more with me, that's great. I mean, that's what I'm here for, is to do these problems, right? So I'm going to go ahead do this one here. But again, if you want to pause, try this on your own and see how far you get. Cool. So, oh, sorry, minus x minus h over 2. So we can go ahead and try this one too. Go ahead and do your DOU. C5, so 2 times 5 is 10 plus 2 is 12. 12 minus 10 is 2 over 2. There is 1 degree. So again, what is 1 degree? That's a double bond, or it's a ring. And again, what do? We see on saturation, go straight to your CNMR. So again, this region here, I wouldn't really even care about. Who cares? This is boring. But look at that. We have a long, long line at 200. Long, long line at 200. And what did we say 200 corresponded to? What do you guys think? Corresponds to ketone aldehyde. So we have very good, very good confidence that this is a ketone aldehyde. Of the two, which one is it likely to be? Look at that 1H all the way down to 10. Who is that guy? That is aldehyde. So this is going to be an aldehyde molecule. And thanks to the CNMR and the HNMR, we are able to solve exactly for that structure. So you can almost even start with an aldehyde. Now, depending on who your professor is, sometimes aldehydes couple, sometimes they don't. In this case, when I threw it in CNMR, it did couple, and it's a 1H triplet. So based off that, we know that there's a 2H here, which is great. So we can label this 2H. So we've already gotten quite a bit of information on this molecule. Okay. Put uncertainty here. This 2H could be a lot of these guys. It's not very intuitive immediately. It's not very helpful immediately. Okay. So could be a lot of these guys. We're not really sure, but we could use a little bit of, a little bit of context to help us out. Mainly the context being of looking at our ranges. So normally when there is a 2H next to a carbonyl, right, where do we say that 2H is? Where do we normally say that 2H is? Normally that 2H is about 2 to 3, right? This guy is a little shy. That's okay. It's okay. It's not a big deal. It's a little shy. It's a pentet, okay? But we'll still include it in. We have a 2H triplet and a 2H pentet. If we use the same logic that we've been using like throughout today, right? This is actually probably easy to solve, the structure here. Oh, shoot. That's not a triplet. That is a quartet. My bad. I will update this. Hopefully you guys caught that. That is actually a quartet. Sorry. I will mention it in the when I post this up. That should be a 2H quartet. It's funny because I went through this like 3 times and I don't know how I didn't catch that. But anyways, a quartet, it doesn't matter. We can actually tell which one is likely to be the correct answer simply by doing this. If it's a 2H pentet, this 2H must have 4 neighbors, right? Which means that there must be a CH3 here, right? Because 3 here, 1 here, that is a quintet, or sorry, a pentet, right? So 5, if it's a pentet guy, it has to be this. You can tell this is wrong because of what reason that we used earlier. Why does this have to be wrong? This has to be wrong because it completes a structure and we haven't even finished the whole molecule. Like there's still so much left of the molecule. 5 carbons and we finish this somehow on 3. It's not going to work out. So that's one way you can tell that it can't be the pentet. For the quartet, right? That just means, again, now we just need 3 neighbors. That would be a CH2 and that third neighbor there. Okay, so again, aldehyde protons can couple. In this case, it did couple. You can see here, and clearly these two had to have coupled. And we can tell that it has to be this guy here. So the quartet is going to be the 2H there. Oh, sorry. This green color. The quartet is going to be this guy here. And it has to be a CH2 that coupled to it. Which now leaves us with this 2H pentet and this 2H triplet. Now, again, it's not entirely obvious which one of the two it could be, because a triplet means that there's 2 neighbors, which there is 2 neighbors here. So it could be that guy. Pentet just means that there's more neighbors. So it could be there as well. I would say, I mean, you can maybe make a good guess as to what you think it is. And personally, I feel like I'm not too confident just quite yet. I know which one it is, but that's okay because there's still one more piece of information we can pull out of this, and we have to look at the formula for this. So in the formula, we have a CO2, right? And one of those CO2s, right, or one of those O's in that CO2 is the aldehyde CO, right? So the aldehyde CO is one of those O's. The other O we never really talked about. Right. Again, CO bonds can present themselves in 2 ways. It can be ethers, or they can be alcohols. Any broad peak? Do you guys see any broad peak? I don't see a single 1H singlet. It's not going to be an alcohol. So it has to be an ether. And once again, where do ether bonds tend to show up? 3 to 4. And what do we see so magically and majestically here? We see a 3H singlet and a 2H triplet. So how do you guys reckon we're going to solve this out? Not very complicated. CH3 singlet, probably going to be something like this. And we have a 2H triplet, which means that we've got, what color do I want to use here? I'll just use this pink one, 2H triplet over here. And again, 2H triplet must mean that, you know, if there is no neighbors there, the neighbors must be there. A triplet means 2 neighbors. There's got to be 2 guys over here. And look at that. We have now solved for all but one CH2. And would it surprise you guys if that green CH2 and this CH2 that we couldn't resolve, or that we just figured out, were the same guy? Shouldn't surprise anyone. Again, this here, if we kind of just like get rid of the uncertain parts, right? This here is all the protons. We know for a fact which one they are because we labeled them. All that's left over now is this one CH2 that's kind of hanging out. So I'll just put them over here, right? There's this one CH2 that's just kind of hanging out. How can we resolve this? Look at this. There's uncertainty here, connected there, uncertainty here, and connected there. And there you go. That is your molecule. So sometimes you can just, you know, leave a CH2, a glue piece of CH2, right? For the end when you figured out all the other important stuff first, which is what we did here. 1, 2, 3, 4, 5. Okay. Another thing I like to think of is that this here, when we have like a column or like a row of CH2s, I call this the sea of CH2s. And this is a very common feature in a lot of NMR, where you see a bunch of CH2s in your spectra. Sometimes those CH2s will be next to each other, especially if they're high multiplicity, like quartet and pentet. Quartet, if you see like a quartet or especially a pentet, because if you think about it, right? If I have a sea of CH2s, the middle CH2 has got to be a pentet at the very least, right? So whenever you see these, if you see a pentet CH2, it's a very good indication it could be part of a sea of CH2s. So again, that's just a term that I use to describe this. And at least in Lieben's class, Lieben's loves the sea of CH2s. Okay, I practically made the term up because of her. Cool, but hopefully this one wasn't too bad. Again, hopefully the logic tracks. And if you need any extra, if you need any extra help with either two of these, by all means, ask questions. Let me know. Unfortunately, you can't ask me them live because you're watching a recording, but you can always contact me, either by email or by Discord. So let me just throw my email down here. This is @Gmail. So you can throw me the email through there, or you can contact me on Discord. That works too. Cool. So let's go ahead. Let's move on. Hopefully feeling good about these. Let's go ahead and do this one. So 2c plus 2 plus n minus x minus h all over 2. If you want, try it on your own. I highly recommend now you guys do these on your own at least once. It's like spend like 10 minutes on it. Like I said, any undergraduate student, if they're doing NMR problems, should only spend 10 minutes on it, right? I don't think any of the last problems took us more than 10 minutes. Maybe it did. I don't know. I'm hoping not. But anyways, spend like 10 minutes, and if you can't, come back and let's do it together. Or if you can, solve it and then see what we get. Cool. All right. So doing DOU here, 5 times 2 is 10 plus 2 is 12. 12 minus 8 is 4 over 2. So we get 2 degrees. So reminder of what 2 degrees means. 2 degrees means we have like a double bond. We have a triple bond, or sorry, double bond and a ring, double bond, ring and a ring, or we have a triple bond. Okay. And so now that we have multiple different types of functionality, let's go look in the CNMR and see what we get. Cool. So looking at this might have been a little difficult to interpret, which is, that's okay. But one thing for certain in all of this is that we cannot have double bonds. Oh, I guess I should have asked what it was going to be. You can look over here. Double bonds have to be 100 to 140. Don't see that. We don't see 100 to 140, those double bonds. So there's no way it could have been any of the double bond options. The ring options could have worked, but remember that about 60, 70 to 100 is where we see triple bonds. And we do see, we do see some lines 70 to 80. So it falls right, just right in the spectra, but we can with some certainty say that there is a triple bond in the structure. Okay. Another thing that we can kind of look for is if it's a triple bond, it could be a terminal triple bond. And terminal triple bonds have a 1H that couples. We do see a 1H here, and we do see a 1H here. So this one is more broad. So actually, I guess we've already now solved for what this O is, since we have a broad OH. But we can maybe say that this triple bond that we have is a terminal triple bond because that 1H triplet. Now, I know that this is a very, very hard thing to say, right? Like you have to really make a guess here. And, somebody could claim, oh, you know what the structure should look like already because you made the problems. That is very true. But, right, there are other things we can look for. So let's go with that. So let's say that there is a triple bond for sure in this structure, right? Other than this 1H, which again, I have to be very I have to say with a little bit of I'm not sure, right? How can I prove to myself that this is going to be the case? Well, remember that little thing that I mentioned about pi bonds? We said pi bonds can do something interesting. They have something called the anisotropic effect. Oh, actually, no, not the anisotropic effect. There's actually something else. There's something else that you can use here. And I realized I should have mentioned it before, but I'll mention it now. This is a great time to mention it. Protons next to pi bonds tend to have complex splitting. So what is a complex split? So if you look at most of the examples we've done before, some of these peaks are really, really nice. I mean, say for this 2H triplet here, right, which is a little bit complex if you had to ask me, most of these peaks were really, really nice. I really went out of my way to make sure these molecules were looking good and you didn't have to worry about anything. But we have a little bit of a weirdness to these peaks, or to that peak. If we look in this molecule here, right, most of these protons look pretty nice, but the 1H triplet and the 2H multiplet look a little nasty, right? If you had to guess, right, you might call this a triplet. I can see why you would say that, but really it's a triplet of doublets if you look very, very closely. Actually, the reason why I call it a multiplet is because you without zooming in, you can't tell this, but if you look very carefully, that's a triplet of doublets. So this is what we call complex splitting. And actually, even this 1H, right, it looks like it's nice, but it's actually a little complex because look at how high that base is. Whenever you see complex splitting, it is always going to be because of a pi bond or a ring, because complex splitting arises from diastereotopism or diastereotopic protons. Okay, so diastereotopic protons cause complex splitting, and one of the common cases of diastereotopic protons are going to be alkene protons and alkenes or alkynes, because they're pi bonds, and pi bonds cause this type of splitting. So a little cool tip and trick there, right? If we wanted to know if there was an alkyne or a ring in this case, right? How do we know? One is we can say that there's a 1H triplet. The other is we can say that look at this 2H multiplet. It's complex, so it's probably next to some kind of pi bond, right? You wouldn't get this level of complexity with a ring. Oh, what did I say earlier? Did I say, no, sorry. I think I said ring and alkyne causes complex. Okay, so ring and alkyne do, but I'll show you what I mean by a ring complex. So there is a way for a ring to do complex splitting, but it is not going to be the way that we see it here. I can see how that's a confusing statement now. So, okay, anyways, I guess another way you can prove to yourself is that there's only 5 carbons. So two rings and 5 carbons is not really going to work, right? Because at the very least, if you want to do 2 rings, it'd have to be 1, 2, 3, 4. I guess you could do a 4. That's really nasty though. Like, where are you gonna put oxygen? It'd have to be a square, I guess, I guess a square and a pentagon, or square and a triangle would work. But pentagon is 1 ring, but you can't really do that. These 2 are really bad structures. No one would ever ask you to solve for something like that. Okay, so that's I guess a better way to explain why it can't be 2 rings. But I'll show you guys what a complex split or a diastereotopic split looks like on a ring, and then you can tell how it's not so much like this over here. Okay, but for the time being, right, this is an alkyne, and so terminal alkyne, because we have a 1H there, and even if we weren't sure, right, we could still make this guess, right? It's a pretty good guess. Unfortunately, terminal alkynes and internal alkynes, IR is actually probably the only thing you can use to tell the difference between them. So you would probably need that information. I'm not sure if you'd be given that, but you could be given that piece of information. Keep in mind that it's like 3200-ish, 32 centimeters, inverse centimeters will tell you if there is a terminal alkyne there or not. Okay, but anyways, let's go ahead and go with that, right? We have a 1H triplet that's kind of complex. We've also got this 2H multiplet, and like I said, this multiplicity, the fact that it's complex is resulting from its interaction with a pi bond. So we can say with confidence that this 2H is probably right here. That's a pretty good guess. So, oh, sorry, wrong color. So we can say this here, right, is over there. And again, if you kind of ignore the complexity of it, you kind of see it's like a triplet of doublets. If you ignore the splitting of an individual peak, you can kind of make an argument. I've seen some people teach this. You can kind of make an argument that if you just ignore the splitting of an individual peak, it looks like 3 peaks, like a triplet. By all means, you can use that. I personally, though, feel like it's a little sketchy as a tip. I'm not sure if I would use it very often. So I'm going to say that there's uncertainty here, but you could, I think for this structure, you can say that this is a triplet and it'll work. But let's try to do this without doing that, because again, I personally can't tell you how often that will be true. And we can still solve the structure without knowing that piece of information. Okay. So as of right now, all we really got are 2 protons down based off of, complex splitting and, the CNMR. What can we tell about the rest of this? Well, like I mentioned before, one of these peaks actually resolved itself very quickly, this broad 1H, because a broad 1H is typical of an OH and or an NH. And look at that, we have an oxygen. So we know for a fact that on this molecule, there is an OH. Okay, so we know for a fact there is an OH. And not only do we know there's an OH, but if there is a carbon bound to this OH with a proton, right, where is that proton going to show up? It's going to show up 3 to 4. We have a really nice 2H triplet. That is amazing. Really, really clean. So I can go ahead and label this 2H triplet. Oops, wrong color. Go ahead and label this 2H triplet just like that. And again, it's a 2H triplet. And carbon protons don't couple with alcohol protons. So that must mean that the 2H's, wherever they are, have got to be over here. Let me use a different color. They've got to be over here. Okay. And so there's only one other 2H left. And look at that. What is it? It's a 2H pentet. You guys remember what we said about 2H pentets? 2H pentets are part of that sea of pentet, that sea of CH2s. And so it shouldn't surprise you then that this is sort of the glue, right? It's this CH2 here that glues this piece to this piece over here. So in this case, if you did ignore the complexity of the 2H multiplet and said it was a triplet, it would have ended up working out. It is actually a triplet if we actually look at, do everything out. But in my opinion, I don't like saying things that I can't for 100% fact say is true. So that's one thing that I would try to recommend against, but it would have helped. It wouldn't have hurt you if you had done that, but we can solve the structure in other ways too. And everything worked out in the end regardless. Okay, cool. So hopefully this works out. And again, I apologize for that confusion on the complex splitting if I did cause any. For sure, right, complex splitting, if we see it, is going to be caused by a pi bond or a ring, but ring complexity tends to be a little bit different. And I can show you what I mean by that. Cool. All right, let's move on. Cool. All right, this is going to be the first really significant example, an example that really captures a feature that if you recognize it, you will always get this. You will always get this right. Okay, so go ahead, do DOU. Definitely do this on your own. I think most of you will enjoy this one. And there's something that you can take from this and remember for the rest of the NMRs you do in 118 for 118B. Cool. So DOU is 2 times 6, which is 12, plus 2 is 14. 14 minus 10 is 4 over 2. There's 2 degrees. So again, what does it mean to have 2 degrees, right? Double bond, ring, 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 or triple bond. So let's go ahead and look in our CNMR. And what do we see? In our CNMR, we see, again, ignore this is garbage, but we see 120, 2 peaks at 120 and 130, and we see a peak at 170. What do those peaks mean? What do you guys think those peaks mean? All right, like let's go back, right? What do we see at, what is 120? We see 2 lines at 120, looks like it's an alkene. We see something at 170. What do we think it is? It's going to be one of these derivatives here. And in particular, look at the formula. The formula is CO2. So what do you guys think this derivative is going to be if it's CO2? It's not going to be acyl halide. It could be the acid, but there was no acid hydrogen, right? So it could have been the acid, but I don't see an acid hydrogen. The acid hydrogens are about 12. And they're also broad, so I don't see that. It's definitely not the amide. It's finally the ester. So I line these up perfectly with or next to each other because I wanted you guys to have an example. Oh, sorry, it would have been this one. I wanted you guys to have an example at least where there's an aldehyde or a ketone and you see that 200 line. And then you have one where it's at 170 and it's an ester. And now everyone's super happy because it's like, yay, like finally something is, hopefully something is making sense. So definitely there is an ester in here of some kind. And definitely there is a double bond of some kind. Now the double bond is probably the easiest thing to work with first because where do double bond protons show up? They tend to show up 5 to 6. And how many protons do we see 5 to 6? There are 3 of them. The reason why I want to do this problem is because I want you guys to recognize this. Anytime there are 3 hydrogens, 5 to 6, right? And really the pattern is the following. So like a generic pattern, you can this one's a little bit different, but a generic pattern you can remember is that there's like a 1H like this. I think there's one more example where I do this. So a 1H like this, and then a 1H multiplet like this. So doublet multiplet. This is always 99% of the time a terminal alkene. A terminal alkene. So how does this work then, right? If it's terminal, how does this work? Well, these 2 protons here that are geminal are the protons at 5. The 1H multiplet mess is this guy over here. So geminal protons tend to show up together at 5. It is the terminal, right? It is the terminal geminals that show up here. Oh, sorry. Yeah, geminal protons, these guys here, these geminal protons show up at 5. Okay. It is this 1H multiplet that shows up all the way over here. Or yeah, over here. It's very deshielded. Okay. Because for one reason, the one reason it's deshielded is because it's around so many protons. The other reason is if you think of the polar, let's say we think of propene, if you think of an appropriate polarization of propene, you probably think of this, right? Secondary cation, primary anion, right? So that's one way you can sort of prove to yourself why certain deshieldings happen, right? If these terminal protons here, right, these geminal protons are shielded, like they're given extra electrons, they should show up closer to 5. This proton here that should have more cationic character on it, right? Because there's a carbocation character on it, so show up more d-shielded at 6. So cool little way to prove that to yourself. So this is a really cool trick. If you see those 3 hydrogens, and again, this pattern here is a pattern you really want to remember. That is the terminal proton pattern. Okay, very, very likely to show up. It's one of the most popular patterns. So I'll go ahead and draw this in. Already figured that out. Now, unfortunately, this 1H could couple to another proton here. I mean, it definitely probably does. It's just a little, a little bit weird because it's a 1H multiplet, so you can't tell how many protons are there. But if you had to guess, right, you have 2 H's and you have a 3H. Which one do you guys think it's going to be? Like if you had to put your money on it, you had one shot at choosing which one it is, which one do you guys think it's going to be? Okay, I think if I had one shot, right, I would put it as one of the 2 H's. Because if you put a CH3 here, again, you've done that thing where you finished the molecule. This is propene, but that's not what we want. We don't want propene. It's definitely going to be, right, one of the CH2s. Now, the other thing too is that you can see that the CH3 is near 1, right? And the CH2s are a little bit higher, right? So then you could also make the argument of like, which peak makes more sense next to a pi bond, right? So next to an alkene, I'll give you an alpha to an alkene. Where do we tend to see protons? So alpha to an alkene, where do we tend to see protons? We tend to see them about 1.5 to 3. So when we go back up here, right? I mean, yeah, I guess, it's almost 1.5. This is not going to count, right? This one's at 3. This one's at 4. Which one is it more likely to be? The one that's next to this pi bond. You don't have to second guess yourself. It is very, very much going to be this 2H here. And you can see also the base is kind of raised on that, right? So it is acting a little complex, right? Because that base is raised on that peak. But it's definitely going to be that 2H over there. Okay, which only leaves us with a 2H and a 3H, which again, you could make an argument as to what goes there. But I would say, again, maybe at this point, I'm uncertain, right? I'm uncertain as to what to do. So I kind of leave it there. I could then look at my ester. And again, the ester has 2 components. It has an ether component and it has a carbonyl component, right? Of these 2, one of these is very easy to solve. That very easy part is the ether part, because ethers or COs, again, we know where COs show up. They show up 3 to 4. And look at that. We have a proton all the way up here at 4, and it is a 2H quartet. So we have a 2H here for sure. And do you guys remember what I told you guys about what we said about 2H quartets? We said 2H quartets that are next to oxygens have always got to be next to CH3s. And those CH3s are always triplets because this is a ethyl piece. And so now we have solved every single proton here. What do you guys think we're going to do? I think we're just going to glue these pieces together and we're going to call it a day. Now, you could also have solved this, right? You didn't have to necessarily go to the ester, even though I think that's the easier way to do it. You could have also solved this by realizing that this 2H doublet can only have one neighbor, meaning that it has to be this guy here. So if the 2H doublet has one neighbor on this side, and all those neighbors are on this side has to have no neighbors, right? Because the 2H doublet, all neighbors on the left side, this side has to have no neighbors. The only way to do that is to put a carbonyl on that center. Okay, so that's another way you could have solved this too. You didn't have to skip over. I just, sometimes that's a hard thing to see. So you can say there's uncertain and move on to a different piece. And again, I think working from this piece on, I mean, there were so many ways you could have tackled this problem. It's a very solvable problem. So cool. Now we have a little bit of a taste of a terminal alkene. And hopefully now when you guys see it, you'll know to solve for it. Cool. I think we're making good time. Should be at least at an hour, maybe a little bit over. So this video won't be too long, just great. How many problems do you have left? You have 1. Oh, we only have 2 more left. So sad. But these 2 are good problems. The last one's a really good one too. Cool. So let's go ahead and do this one here. Oh, this one is going to be interesting. This is going to be interesting. Cool. Okay. All right. Do your DOU. Hopefully, or try it on your own if you want to. And if it's a little bit hard, which I imagine this one will be, right? Don't worry, because this one had something in it that I needed to remind you guys of because it's the one thing we always tend to forget in this class. Okay, cool. So let's go ahead and do DOU. 2c plus 2 plus n minus x minus h all over 2. 6 times 2 is 12 plus 2 is 14. 14 minus 8 is 6 over 2. We have 3 degrees. That's a lot of degrees. 3 degrees tells us that there's a lot of things going on. We could have some kind of 1 degree thing going on. Or we have some kind of, we have a 1 degree thing going on with some combination of 2 degree. So a lot of stuff that we got to write out here, but it's okay. Don't worry. We can use our CNMR, our advanced IR, to help us out a little bit. Okay. So looking at this, right, I can already see a couple of things, right? Again, ignore the stuff here. No one cares. Look what we got here. We've got protons. Looks like we have something going on 130-ish. 1, 2, 3. We have something on 130-ish. Oh, we've got something going on 160-ish. Oh man. Okay, I've got to make another note because, oh, you know what? But you can reconcile this a little bit. So okay, so I can see how this might be misleading here. This might make you think that it's a acyl derivative. I should have thought about this before I wrote this problem, so I apologize. But you can kind of tell that things are a little bit awry because remember, you need pairs. You need pairs of carbons in order to solve this as an alkene. So both of these would have to be paired together. There also isn't any symmetry. So you know that one line can't be 2 of them, right? Or I guess, I mean, there's 6 carbons. Maybe you could have made an argument. I don't know. But I'll make a note that for a C6H8O or for the 5th problem, I'll make a note that those two, I'll just have to tell you that those are the alkene carbons. But this does contain something that's interesting. So this might have been confusing, so I apologize. I know it falls in that 160. And a couple of you probably got really confused as to how to deal with that. But this is 2 of these are going to be alkenes. This at 200 can be ketone or aldehyde. Definitely going to be ketone because there's no aldehyde proton. Cool. So right now we have ketone aldehyde. Sorry, we have ketone and we have double bond. Alkene, but that's only 2 degrees. That's only 2 degrees. So that must mean that there is a 3rd degree in here, but it can't be a functional group because we would have seen it, right? Any unsaturated functional group we would have seen in the CNMR. So then what does this got to be? If it's not a double bond of some kind, what does it have to be? This has to be a ring. So that's crazy, right? Made it a ring. This structure is going to be a ring structure with these guys in it. Just wanted to remind you guys that rings are the hidden degree. They are the degree that you look for everywhere and you can't find it. There's nothing in the world that will tell you that something is a ring. The only thing you can look for is a degree that you can't resolve. So I guess in a sense, it's something you can't look for, right? If you can't find something to resolve a degree, it's got to be a ring. Now, based on the carbon count, I was really lenient on this one. You could have checked, right? You could have tried a C6 cyclohexane, and maybe well, actually, let's start with the hexane first. Hexane you can immediately debunk because although you can't have 1H's and 2H's, so somehow you could have done 1H, 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 2H. The one thing you can't do is a 3H. So keep in mind, on this cyclohexane, you only allow these 6 carbons. All 6 of these carbons can only be CHs or CH2s. You cannot have a ring carbon that is a CH3. Now you could have a CH3 coming out, but that's not 6 carbons, that's 7. So it cannot be cyclohexane that is the answer here, which leaves us with our next possibility of cyclopentene, right, or cyclopentane with a CH3 sticking out. This is 5 carbons and a CH3 sticking out just like that. So you could have done that. That could have worked, okay? But at the very least right now, we know we have some kind of cyclopentane. Now, on top of there being a cyclopentane, right, once again, we're kind of sticking with the fact that there is a CH3 sticking out, or that's a good guess to make, right, that we could have made here. And this works also really well because it's CH3 doublet. So if it's a CH3 doublet, it must be next to a 1H, and there are several 1H's here, right? This 1H could have been one of them. So there is a 1H somewhere, right, that this one could have been next to. So that works too. Okay. One thing to note here is that this CH3 is pretty low on the electronegativity, right? Or it's on it's low on deshielding, so it's not next to anything electronegative. is probably just connected to another carbon that's very, very, boring. Okay. But now we have to figure out, how do I fit in a ketone and how do I fit in an alkene? So this is where this problem probably got really, really hard. It might have been very difficult to proceed at this point. And so that's why it's really good to know our tricks. Okay. It's really, really good to know tricks, because tricks can really help you out here. And the trick that I want to teach you guys here is the trick of these protons. So looking at these protons, it might have seemed like they were aromatic because they're at 6 to 7. But if we think about aromatics, remember, not only is there proton 6 to 7, but that must mean that our 100 to 140-ish range would have a band of carbons. So in order for this to be benzene, there must have been a band of carbons here. We don't see that. We only see one carbon in that range. So it can't be that this was a benzene that was causing these. This still has to be an alkene. But if, normally it's 5 to 6 and now it's 6 to 7, this alkene has to be very, very deshielded, meaning this alkene has to be next to something that is electronegative. If we think about the components in our system, right? We have a ring, we have a alkene, and we have a ketone. What do you think the ring has to be next to for it to be so deshielded? What's the other electronegative thing? The answer is the alkene, wherever it is, must be next to the carbonyl. It has to be next to the carbonyl, because the only electronegative thing in this system is the carbonyl. And if the alkene is being so deshielded, right, it must be directly next to the carbonyl. In this case, it's actually conjugated. All the p orbitals are next to each other. This structure here is known as an enone, and enones sometimes get asked on the exam, which kind of sucks. The one thing to know is that enones do very crazy things in the NMR. In the HNMR, right, they tend to show 6 to 7 ppm. And in the CNMR, do you have the same phenomena where we have a carbon that's so deshielded, it shows up in the acyl derivative range rather than the alkene range. So you tend to have one that's 120-ish and one that's 150-ish. Okay. Point is that look at this separation between these two, right? One is at like 120, 130. The other is at like 160. Okay. So that's the point with the enone. Again, main reason why I brought it up is just because sometimes it gets added in. The reason why I brought it up is that it gets added in sometimes for the questions on an exam or on a practice sheet. It's just a good thing to know. And I wanted to show this trick to you guys. This is more relevant for the end of 118B, but it's still a trick that's good to know. Okay. Now, another thing, so let's just talk about features in general on this, right? Another thing here that you might have noticed is that there is a 2H2H, but there's a 2H that has two separate peaks. That's kind of weird, right? Because you're thinking, oh, did you mess up here? Did you like mean to put 2H and 2H? No, this is actually a 2H. It's just separate. Each proton, that 2H, is represented by each of these peaks. This is also another form of a diastereotopic proton, right? And it's the kind of diastereotopic peak that you see for rings. So rings tend to have like symmetrical, like you can see it's kind of like leaning on itself, right? Like that's the way I think about it, is like it's sort of like mirroring itself in a sense, right? That's how you can tell that there is a ring sometimes, is if you see this here. Now, once again, I'm not saying that if you see this, it has to be a ring. I'm just saying that if you think there's a ring and you see this, it's a very good guess you can make, because diastereotopic protons on a ring tend to do this weird like mirroring thing. Okay. So there is a CH2 on here, this one here actually, that it's exhibiting that diastereotopism. Okay. So it's going to be that guy there. Now that must mean then that the 1H that we figured out earlier, which is the only 1H it could have been, is this guy here. Okay. And you can see that this guy is relatively up there. Okay. So a very good question that comes out of this then, right, is, okay, so so hopefully I understand now why the alkene is deshielded, or is deshielded. So it has, like, why it's next to the ketone has to be deshielded, right? I understand the 2H is the diastereotopic, but how did you know that the isomer was the enone with the methyl next to the carbonyl, and not the isomer where the enone, or the enone isomer where the pi bond was next to the methyl? So how do I know that the methyl was here? And that's a great question. It's really going to boil down to figuring out the difference between this proton and these protons, right? We have to think about what would those protons look like in the HNMR if they were if they were where they are. So what I mean by that is, well, first off, we can think about this, right? This position here next to the, so let's talk about this position. This position here next to the carbonyl, right? So we can think of that as next to a carbonyl, okay? And then this position here, right, next to the pi bond, we can think of next to an alkene, right, next to a pi bond. Which position do you guys think is more deshielded? So just take a guess. Which position do we think is more deshielded? Do we think the ketone is more deshielding? Do we think the pi bond is more deshielding? So it's not too difficult to reason this if you just think about the electronegativity. But if we think about the electronegativity of a carbonyl, that is very, very high, right? It's a carbon O double bond, and carbon is losing out very hardly. It's very hard to O, right? O is a way more electronegative than carbon. There is a very big dipole there, which means that this position here would be pretty big in terms of a delta positive, right? Big for dramatization there. On the other hand, CC, right? That's a little more, less electronegative, more non-polar, not too crazy. This position here, although there is a difference between sp2 and sp3, right? sp2 carbons, right, are not going to be that deshielding. This is not going to be that high. So of these two protons, where one is very high and one isn't, you can make the reason that because the 1H is all the way up here and the 2H is all the way down here, this guy must be deshielded, this guy must be shielded. Meaning that the 1H has to be next to the more electronegative pi bond, the carbonyl, and the 2H diastereotype particles have to be next to the less electronegative pi bond. Right there. So this problem actually ended up being, I think this might have been the hardest one now that I think about it. This problem was really, really hard. And there's a lot of things you can use to help you out, but I think knowing the trick now can really help you guys solve this problem. And also knowing this little tip here, right? Sometimes two different isomers might look like the same answer. How can I reason to myself why one is better than the other? Cool. I imagine there will be a lot of questions on this one, so feel free to ask me as much as you need to on this. I actually really like this one, but it might have been too hard. And this is more like the final level, like NMR. So if you solved it, that's great. You can solve the final level NMR. Cool. Last one here. Let's actually go through this one quickly altogether, just because I want to end this off. I think I'm hitting the hour mark soon, which that's a great thing. Or maybe I went over. I'm not too sure. Anyways, let's just solve this one really quickly together. There's a lot of things going on. Always look at your scale, right? The scale is like a lot different from the other scales. So make sure of that. The DOU of this, I actually should already have calculated in my head. Should be 4, 5. It should be 6. It should be 6. And the reason why I say it's 6, okay, so I'm pretty sure it's 6, and we can reason this out a lot. One thing we can notice is that, oh, look at that, we have a acyl derivative, right? 160 to 180. And again, we can tell what it is because when we look at the formula, it's a CO2. So it's an ester or an acid. Look at that. We have a broad peak at 12. It's going to be a carboxylic acid. So there's a carboxylic acid in here. That's 1 degree. What did I tell you guys about a band of carbons from 100 to 140? What is a band of carbons? And also activity from 6 to 8 or 7 to 8 in this case. This is going to be a benzene ring. So I have introduced in this one here a benzene ring. You can actually even think about, right, there's how many protons are here? There's 4 of them. So that means that we have 4 splitting patterns available, or 3 splitting patterns available. So we have the ortho, meta, and the para. Remember, thinking about the splitting patterns, right? If these two groups are different, right, para would be two 2H towers. I don't see 2H. It's not going to be that. Ortho is a complete mess of 4H. I might see that, but meta has a 1H singlet. And if you look here, I mean, it's, it really looks like any of these could be a 1H singlet. So my best guess then is that this is going to be a meta coupling, not an ortho, just because I know ortho in general is really, really nasty. Okay. But yeah, I'm going to go with the meta coupling. Now I just need to solve this out. Okay, so I'm just going to put all of these protons in the same color, just for the sake of time. But these 4 are those guys. We'll put red here for the carboxylic acid. I don't really know what's next to the carboxylic acid at the time being, but I can come to figure out 2 things got to go here. So now all I have is this stuff here. Now there is another relationship in here that we just saw a couple while ago that should help you out. 5 to 6, I have 3 protons. I mean, am I really going to guess here? Like it's very clearly, it's got to be a terminal alkene. So I'll separate these out a little more in color. But yeah, we know this is a terminal alkene. We learned that earlier. So we figured that out. So all that's left now is a CH2 doublet that's going to act as a glue for some piece. So here's the point, right? This is a meta split. This is some sort of meta coupling. So there's group going here, group going here. And you can think of many ways to put this together. I'll tell you this, it's definitely not this and this. It can't be that because you missed out on the CH2. So on one of these groups, you've got to add the CH2. What do I mean by that? What I mean is you got to do either this joining here, so the CH2 goes with the acid, or the CH2 goes with the terminal alkene. Okay. For those of you that are having a hard time seeing that, let me just draw it out really quickly here. I'm basically saying you either have this or you have this. Okay. I'll give you a hint. Based on the fact that this is a 2H doublet, you can tell which one this is for sure. Okay. So let's give this a color and let's quickly solve. So if this 2H is the one we're concerned with, which one is the one that would give us a 2H doublet? Don't think about this for more than 30 seconds. It's very simple. This guy has no neighbors here, no neighbors here. So could that give us a 2H doublet? Not at all. It has to be this one down here. Cool. So I know I went through that one very, very quickly. I apologize. But again, I just wanted to make sure I got this out very quickly. I think this one was actually very simple. It has a lot of lines, but it's pretty simple actually. Not too difficult. I think actually really this one was the difficult one, so I should switch it over. Cool. So hopefully this helps out. If not, please let me know and I'll try to do better. You know, if you guys don't tell me that I'm doing bad, I can't, you know, improve. Hopefully these problems help you. Don't let these problems freak you out. These problems were intentionally harder than what you're probably going to get because, you know, it's meant to just, you know, push you in the hardest way possible. Cool. I'll make a note of that one thing. What did I say I wanted to make a note of? I made a mistake somewhere. Where did I make a mistake? I forgot. I remember I said somewhere I wanted to, oh, I think here, right? I think I said I wanted to mention this, like mention that for problem 5, the 2 lines around 150 are alkenes. So I'll give you guys that much information. Yeah, cool. I think, is there anything else I want to say for this one? No, yeah. Okay, cool. All right, yeah, let me know how this is. And let me know if you need more help. See you guys later.